Hello and welcome. This is SFU Math 232 Linear Algebra. My name is Brenda Davison. So today we're going to cover section 3.3, Elementary Matrices. And coming with that is then going to be a method for finding a matrix inverse. So really that is the main thrust of the lecture today, is that if a matrix has an inverse, we want to be able to figure out what that is. So this is going to be a method of finding the inverse of any square matrix. A matrix that is not square does not have an inverse. It might have a left or right inverse, but it does not have an inverse where a to the minus 1 equals I, and a to the minus 1 a equals I. Okay, so it's sort of like having a left or right limit, but and then them not agreeing, and then not having a limit. So they need to be square to have an inverse, and we're going to figure out how we can do that. Okay, to do this, let us just recall a couple of things. What are our elementary row operations? So we started out this whole course with the idea of solving a system of linear equations, and then we had row operations that we used, and there's 3 row operations that do not change the solution set, and those are elementary row operations. They are this one. First one is swap 2 rows. That doesn't change any, that keeps the thing the same, and I've been indicating that typically like this. For an here's an example: row 1 switched with row 2. Multiply a row by a constant. So we can multiply both sides of one of our equations by a constant. For example, this would be row 2 becomes 1/2 row 2. So I would multiply row 2 through by a half. And the most complicated of the 3 is adding a multiple of one row to another. Okay, so for example, row 2 could become row 2 minus 3 row 1. Okay, so now what we're going to do, we know these row operations. What we're going to do then is recognize that we can actually set up a matrix that when we multiply our matrix A, for example, of our coefficients of our linear system, when we multiply this matrix by what we're going to call an elementary matrix, which we can capture one row operation in a matrix, and then when we multiply by that matrix, it will affect the row operation on the matrix. Okay, so an elementary matrix is a matrix that results when any single elementary row operation is applied to the identity matrix. Okay, so let's take a look at these matrices here and see if we can recognize which one of them are elementary matrices. And then what we're going to see is when we multiply one of these elementary matrices, it affects the row operation. Okay, so here, this one is an elementary matrix. Tick, it is. Why? Because this thing here, we have basically an identity matrix with the exception of this guy here, and that is row 3 is multiplied by minus 2. Okay, so that has one elementary row operation applied to the identity matrix. Tick, this one is, you could think of this as one row operation, row 1 multiplied by 1, for example. This is an elementary matrix. What has happened here? Which of these 3 things has been applied to I to give us this? Row 1 and row 3 have been swapped. Okay. All right. Is this an elementary matrix? No, it's not an elementary matrix because you have to apply 2 row operations to I in order to get this, and we note this important word here. So it's when you apply a single elementary row operation to the identity matrix. Here you would have to multiply by row 1 by 2 and then multiply row 2 by 2. So that one is not an elementary matrix. How about this guy here? No. Why? Because you'd have to swap rows 2 and 3, and you would also have to multiply that newly swapped row, the row 3 there by minus a quarter. Okay, so the 2 row operations. How about this guy? Next guy over? Yes. Yes, because row 2 is, if I consider the identity matrix, row 2, I would take the identity matrix, I would switch row 2 with -2 row 3, and I would end up with this guy. This one, no. Two row exchanges are required. Okay, so now let's take a look at it. We've got here this elementary matrix right here, and it is the identity matrix with rows 1 and 2 swapped. Okay, so what we're going to notice is if we take this matrix E, 0, 1, 1, 0, and we multiply it by this matrix, the matrix A there, perform this multiplication, and this is what you get. Okay, you see that this result here is A, the original A, with row 1 and row 2 swapped. And this, what we multiplied by, was the identity matrix with row 1 and row 2 swapped. So taking our elementary matrix and applying it via multiplication to our matrix performs the same operation on the matrix as what we've encoded here in the elementary matrix. Okay, let's take a look. What does this, what did I have to do to the identity matrix in order to get this E here? Well, I would have had to have taken R1 and replaced it with R1 minus 3R3. Okay, that would get me the, if I took the identity matrix and performed that, I would get that matrix there, E. I am now going to multiply E multiplied by A. Okay, so I'm going to perform that multiplication, and what's going to happen, I will get these numbers, -5, so that's the first row into the first column, 1 minus 6, giving me the -5. Okay, I performed that arithmetic. Okay, and I see that rows 2 and 3 are unchanged from what they were before, and that row 1, this guy here, row 1, let's take a look here. This is row 1. So if I take that row 1, 1, 3, and I subtract 3 times row 3, this is row 3 here. So I'm going to take 1 minus 6, I get the -5, and 3 minus 3, I get 0. So I have taken this matrix A, and I have produced this row equivalent matrix here, performing the row operation encoded in this elementary matrix. Okay, let's do the final example. So this one was swapping 2 rows. This one was adding a multiple of 1 row to another. This one is multiplying a row by a constant. So we've got, we could see that this E here is the identity matrix with the second row multiplied by 5. So this is R2 as R2 times 5. If I consider what to do to the identity matrix to get E. Then I have a matrix A, and I'm going to multiply E times A. Like that. And I am going to get this matrix here. I perform the multiplication. 2, 1, 3. Row 1 does not change. Row 2 becomes 5, 0, 5. 5 times row 2. And row 3 does not change. Okay, so this, multiplying this A by this matrix E, performed that row operation for me. Okay, so let us just state a theorem here. Suppose A is an n by m matrix and E is an elementary matrix obtained by applying a given elementary row operation to the identity matrix of the correct size. Then the product EA is the matrix that results when the same row operation is applied to A. We just saw 3 examples of that theorem. So let us take a look here. We're asked, find an elementary matrix that converts A into reduced row echelon form. So I look at this, I identify the leading variables. That would be this guy, and then I'm thinking, okay, what do I need to do in order to get this thing into reduced row echelon form? I need to make this guy into a 0. So I decide what row operation that is. That is going to be R1. It needs to be replaced with R1 plus 3 times R2. Okay, so I'm going to now take the matrix I2. That looks like that. And like that there. And then I'm going to form an elementary matrix E, which is going to look like this. I'm going to take this guy, and I'm going to take R1 plus 3R2. So that's R1 becomes R1 plus 3R2. R2 is being left alone. A single row operation like that. That is a single row operation on I2. This row operation there. Okay, then I'm going to take that E and multiply it by A. I take E, it's 1, 3, 0, 1. I will multiply that by A, like that. I perform the multiplication, I get this. There. Now I have a matrix that is in reduced row echelon form. We have leading variables there, and we have on the columns that have leading variables, we have zeros everywhere else. So I have now found the elementary matrix which converts A into a reduced row echelon form. It is this matrix right here. Okay, so the next point we want to make about these elementary row operations is that they can be inverted by other elementary operations. So we can get back by doing something. So we have our 3 potential row operations that we've been using. They are listed here, 1, 2, and 3. And then here is listed, what do you do to reverse that? So let's just give a quick example here. Say we had an elementary matrix that looks like this. Okay, that elementary matrix, when I apply it to some matrix A, will switch rows 1 and 2. Now, if I want to restore this matrix to I'm being told what to do. So this is the original operation, switch rows 1 and 2, and then it says do it again. So I would simply multiply this by this here, and I would see that given a matrix that switches 2 rows, if I multiply by another matrix which switches those same 2 rows, I get back to the identity matrix. That means, because this is the identity matrix, that means this is, if I call this guy here, this guy here E, then that means that this one is the inverse. Okay. Similarly for the other 2 operations. And this one, if we multiply by a constant, we multiply through by 1 over the constant. And if we add a multiple of one row to another, we subtract the same multiple of that row from the other. Okay. So we have the situation that I illustrated up here, that if we have E corresponding to some certain elementary row operation, and if E naught corresponds to the inverse elementary row operation, it is the case that E times E naught is I, and E naught times E is I. This is a case that it doesn't matter in which order you multiply them. This commutes. This is a special case. In general, as we've been discussing, matrix multiplication is not commutative. When the matrices are elementary, though, it is a special case and it does commute. Okay, let's just take a look. We'll take two matrices here. 2, 0, 0, 1. Okay, that's my E. Now, if I was to apply that to a matrix A, I would expect that it would multiply the first row by 2. So then how would I undo that? I would simply multiply the first row by a half. Okay, so now when I combine these two, I expect that the impact on A is going to be nothing. It's going to leave A unchanged. That means that the product of these two has to become the identity matrix. So let's just see if that's the case. We perform the multiplication. We see that is the case. Okay, so if I were to multiply A by this, and then I multiplied by A by that, I would find that A remained unchanged after the second multiplication. Let's just do another example. Here's a matrix E. This matrix is the elementary row operation of taking the first row and subtracting from the first row minus 2 times the second row. So my instructions in my table here for how to undo that operation is to take the first row and add 2 times the second row. So now I'm going to go ahead and multiply these two matrices together. And what do I get when I do that? I get 1, 0, 0, 1. Okay, I get the identity matrix. So I'm back. Okay, so we have an important statement here. All elementary matrices are invertible, and that the inverse of an elementary matrix is also an elementary matrix. Okay, we're not proving that theorem, but that is an important statement, important facts to bear in mind. These elementary matrices are nice at some level. Okay. We've got an important theorem which we're actually going to build on. So there's 3 parts to this theorem, which is basically that these 3 statements are equivalent. We're going to actually build on this and add more statements. Then we have 7 or 8 statements that are all equivalent. Some of them are obviously equivalent. Some of them it's not so obvious that they are equivalent. But once you have one of them, then all of the rest of them are also true. Okay, so let's take a look. We take a square matrix. Important to note that, square. And we're saying that if the reduced row echelon form of A is the identity matrix, then A can be written as a product of elementary matrices, and A is invertible. It's more than that, though, because I can read this in any order. So I could say if A can be written as a product of elementary matrices, then the reduced row echelon form is I, and A is invertible. Similarly, if A is invertible, then it can be reduced to I, and it can be written as a product of elementary matrices. So we want to be able to prove this, and so what we want to prove is what I was saying there. We want to actually, this is what we want to prove. We want to prove that A implies B. We want to prove that B implies A. We want to prove that A implies C, and that C implies A. We want to also prove that B implies C, and that C implies B. In order to do that, we can do this much more. We could do all 6 of them directly if we wanted to, like that. That's quite a bit of work. You can speed this up. This chain of implications that we want to show, we can do that by showing that A implies B, and then we will show that B implies C. Then we will show that C implies A, and then you're done, because you can always go from one to the next. If you then wonder, oh, does C imply B? You're like, well, C implies A implies B, so therefore looping through, B implies C. Okay, so you get them all by proving this statement, by constructing the proof on this statement here. So we want to show that A implies B, B implies C, and C implies A. Okay, so in order to prove that A implies B, that's where I'll start. Let us first prove that A implies B. Okay, that's what I'm doing. So I then assume A and show that B follows. Okay, so given that the reduced row echelon form of A is IN, then I want to do something and show that A can be written as a product of elementary matrices. So that is my the thing that I want to show. Okay. If A can, if the reduced row echelon form of A is IN, then that means there's a series of elementary row operations to take A and turn it into I. Okay, so then there exists E naught, E1, E2, how many ever you need, up to M of them, to take A into I. Okay, so it looks like this: EM dot 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 all the way down, E2, E1, E0, and then A equals to IN. Okay, we already have a statement from earlier, a theorem from earlier. Every EI has an inverse. Let me label that EI to the minus 1, which is also elementary. Previous theorem. Okay, so what I'm going to do is take this long chain of multiplication here, this, and I am going to multiply both sides by EM to the minus 1, like that. Okay, and then you can see that on this side I just end up with EM to the minus 1, and on this side these two things combine to give I, and I'm down by 1. So then I will just do the next one, the next one, the next one, the next one, and so then that means that after I've gone through this whole thing, A will be left here, and what will I have here? I will have E naught to the minus 1, E1 to the minus 1, all the way down to EM to the minus 1. Okay, when I multiply by I, nothing happens. So I am done. So A implies B. I started with the fact that the reduced row echelon form of A was the identity matrix, and then I showed that A can be written as a product of elementary matrices. These are all elementary matrices. Okay, so that's A to B. Now I'm going to show B to C. Okay, that is, I am now starting here, given, I'm starting with statement B, given that A is a product of elementary matrices. I'm just going to put them, it doesn't matter that it's not the same exact list there, but it's a product of some number of elementary matrices. That's what I am allowed to start with. And what I want to show is that A is invertible, that A has an inverse. So what I do is I'm able to start with my given thing there, and I know that E naught has an inverse because it's an elementary matrix, and all elementary matrices have inverses. So I simply go like this: E naught to the minus 1 times A. So I'm multiplying, I'm actually going to be a little bit more careful. I'm going to multiply here, e naught to the minus 1, and I'm going to multiply here, e naught to the minus 1. Okay, so here I will be a times e naught to the minus 1, and that will be em minus 1 dot dot dot, and then this becomes I, so the last one here is e1. All right, so what do? I just keep doing this for all of them. And I end up at the end that I end up with a product of these guys here. I end up with a e naught to the minus 1, e1 to the minus 1, etc., all the way down to em to the minus 1 equals to I. And then I just look at this and I think, okay, a times something is I. This something is the inverse of A, because that is what it means. If you take a matrix and multiply it by another matrix and it comes out to I, then that matrix that you multiplied by is the inverse. Therefore, A is invertible. And I'm finished with that. Okay, now just to conclude this exercise, I have to show that C implies A, and then we're finished. Okay, so I'm now able to start in this one, given that A is invertible. Okay, I'm now allowed to start with that, and I want to show fix that, invertible. I want to show that the reduced row echelon form is I. So I'm going to start with it being invertible. Okay, that means this, A, the minus 1A is equal to I. A has an inverse. And I'm going to say, well, the reduced row echelon form of A has got to be some matrix. Let me call it R. Now my idea is to show that this is I. Okay, so I'm going to take A, do my elementary row operations. I will conclude in a reduced row echelon form, and I, given this statement, want to show that that reduced row echelon form is I. Okay, so I mean, what does it look like? We do a bunch of row operations. On A, and we get to that reduced row echelon form. I know that these are all invertible. I also know that that is invertible. Okay, so now I've got a product of invertible matrices. So that means that R is invertible. But R is reduced row echelon form. And so there's, so let me do it, R is in reduced row echelon form. Okay, and so we have two possibilities. It's in reduced row echelon form, so that means it could be equal to I, or it could have a row of zeros. Okay, that's possible in the reduced row echelon form. However, it is invertible, which means that it cannot have a row of zeros. So that means that this matrix R is the identity matrix, and we have shown A, that the reduced row echelon form of A is I, because now we have shown that this is I. Okay, we've been using this sort of without maybe explicit statement for a while. Two matrices that can be obtained from one another by a finite sequence of elementary row operations are called row equivalent. And I've been using this tilde symbol. This matrix tilde that one, and I've been applying the row operations. Okay, we're going to use this information to be able to take a matrix A and find its inverse. So this is our inversion algorithm. We have a square matrix A that's invertible. The reduced row echelon form of A is I, and therefore there's all these elementary matrices that exist. and A is in fact the product of the inverses of all of those. So now I take the inverse on both sides here, like I take this thing here, I take the inverse of both sides, and I see that the inverse of A is the very row operations that I use to reduce A applied to the identity matrix. Okay, so what am I going to do? I'm going to use this as my algorithm for finding an inverse. Let's see how this is done in practice. I want to calculate the inverse of this matrix. So I form what I'm going to call a compound matrix. It's going to look like this: 2, 0, 0, 0, 4, 3, 0, 1, 1. And this is a 3 by 3 matrix, so I'll use the 3 by 3 identity matrix like that. Okay, now I'm going to go through applying the elementary row operations to take this portion here, A, and turn it into I. At the same time I'm doing that, I will be applying the same row operations here, and it's going to turn this I into A to the minus 1. Okay, let's watch how this works. So the first thing I'm going to do is take R1 and replace it with a half R1 in order to get a 1 there in that first row. Okay, so I'm going to apply that to the entirety of row 1. 1, 0, 0, 1 half, 0, 0. Multiply row 1 by a half. Okay, then I've got the leading 1 here. Now my next objective is to get that to be a 1 there. I'm going to choose to do that by taking row 2 and multiplying it through by a quarter. I'm going to take row 2 and replace it with 1/4 row 2. That's going to get me a matrix. It's my tilde. Get me this matrix here. I'm not changing row 1. Okay, I'm multiplying row 2 by a quarter. I am not changing row 3. Okay, then I have now 2 leading ones, and I see what I need to do next. I've got a leading 1 here and a leading 1 here. Then I need to get a 0 right here. Okay, so I do my next row operation in order to do that, and that row operation is taking row 3 and subtracting row 2. Okay, so I'm going to take this one and I'm going to take row 3 and I'm going to replace that with row 3 minus row 2. Okay, I will do that right now. I will get this row 1 unchanging, 1, 0, 0, 1 half, 0, 0. That's the point you're saying to yourself, thank goodness for computers. 0, I'm not changing row 2. And then row 3 is changing. I am replacing it with row 3 minus row 2. That gets me this here, 0, 0, 1/4, 0 minus 1/4, and 1. Okay, I'm almost done. I have 2 leading ones, and then I need to get this thing to be a 1. So I just multiply the third row by 4. Okay, so I'm just going to proceed to do that, and then write out the thing here. Here is what it looks like. Multiplying that thing through. Oh, I'm not totally finished. I'm multiplying through by 4. Okay, I lied. We have to do one more step after that. Okay, then my final task is, because I want this to be in reduced row echelon form, every column with a leading 1 has to have all other entries be 0. So I am looking at that 3/4, and I need to fix that. And so I'm fixing that in this manner. I am taking row 2, and I'm going to replace it with row 2 minus 3/4 row 3. Okay, I'll go ahead with that. That's going to get me this guy here. 1, 0, 0, 1/2, 0, 0, 0, 1, 0, 0, 1, minus 3, 0, 0, 1, 0, minus 1, 4. Okay, I stop. This thing here is now the identity matrix. So then I claim that the inverse of A is this side over here. 1/2, 0, 0, 0, 1, minus 3, 0, 1, minus 3, 0, minus 1, 4. Okay, now I could check. You can, at least you can check your answer at this point, right? You check your answer. You want to multiply A times A to the minus 1. You are expecting to get I. If you don't, something has gone wrong. So let us try that out. A was 2, 0, 0, 0, 4, 3, 0, 1, 1. And then I will multiply that by the inverse that I have found and confirm that the product is I. Okay, what do I get? I get 1, 0, 0, 0, 1, 0, 0, 0, 1. Yeah, there, confirmation that there's no arithmetic mistakes there. Okay, so now let's take a look at this in the context of our systems of linear equations. We are able to write our systems of linear equations in this compact format. The coefficient matrix A times the vector x is equal to the vector b. The coefficient, this x is the column vector of the unknowns, and b is the column vector of the right-hand side of our equations. Okay, now I could take this equation ax equals b, and then immediately write down by that x is a to the minus 1b. I just multiply on the left both sides by a to the minus 1. So we have a statement here then. If ax equals b is a linear system of n equations and n unknowns, that's important. That means that the matrix is square. And if that square matrix A is invertible, then the system has exactly one solution, and it is this guy here. Okay. Okay, next theorem. If we have a homogeneous linear system, then the solution has the trivial solution if and only if the coefficient matrix is invertible. Okay, this is actually fairly straightforward to prove. So we'll do it. We have to do it, of course, both ways. So going in this direction, we will assume that A is invertible. Okay, and we have the linear system AX equals 0. We will multiply on both sides by the inverse. We're allowed to do that because we have here that the thing is invertible. So we're multiplying on both sides. Okay, and this is simply 0 here. And then that means that x equals 0, not the trivial solution. Okay, so if A is invertible, then the linear system AX equals 0 has only the trivial solution. That's one way done. Okay, then we're going to go the other way. assume only the trivial solution. Okay, we're going to assume the trivial solution. That means if I have a system of linear equations looking like this, yeah, there's some number of these guys. There's one of them, one equation. There is n unknowns, and there's n of these equations, as we are in the n by n case here. There they all are. So these are all my equations. If I have a linear system like that, it's homogeneous, and it has only the trivial solution. That's our assumption. It only has the trivial solution. Then the reduced row echelon form of the augmented matrix is this. All the way down to where we were here. Okay, because made an error there. So so we have the situation. All these ones are going over to 0. Just make this really clear. And I mean, this is the what the reduced row echelon form must look like if there's only the trivial solution, because this would tell me that xn, this bottom row would be xn equals 0, xn minus 1 is equal to 0, etc., all the way up to the top one here, which is x1 equals 0, which is what we know has to happen. Okay, we also know that there's elementary row operations in order to transform A into this thing. Okay, so we took A, we would take A. What I'm saying is we could take A. Here's A. A square matrix. There it is. And we are able to use elementary row operations to make A row equivalent to this matrix here, which is the identity matrix. So the reduced row echelon form of A is I. Then by our previous theorem, A has an inverse. Okay. Okay, some important facts about inverses. We were given two square matrices, A and B. And B is an inverse of A if AB equals I and BA equals I. Okay, when two matrices are inverses and you're going to multiply them, you multiply them either way, you get I. And the following theorem shows it's enough to satisfy one of those conditions. So it's basically saying if one of them, if this is true, then they're both invertible and the other one is true. Okay, so let us just do that. I'm going to do it on one of them. There's an or here. I'm going to do this one of the or, and then the other one follows totally similarly. Okay, so consider the homogeneous system. That would be AX equals 0, for which some X is the solution. Okay, we have that BA is equal to I. That is this here. Let me just, BA is equal to I. Okay, I'm going to take that, and then I'm going to say, I'm going to multiply on the right by X, both sides, and then I'm going to associate this way. And that would mean that we know that this is 0, and that is X. And the only solution is the trivial solution. Okay, so we started from the BA is equal to I, and we found out the only solution to the homogeneous system is the trivial one, and that tells you A is invertible. And that means that, well, okay, A is invertible. It tells you A is invertible, and we had that BA is I, and therefore that B has to be the inverse. And you do similarly for B. Okay, we just showed that A is invertible and that B is its inverse, so you can do the exact same argument in starting out with AB equals I. Okay, a final unifying theorem that catches all of these things. We're sort of been building up. So this is an important theorem. You should be familiar with the results of this theorem. Okay, we have already proved A through D. Done. Proved. Okay, so let us just read the theorem. We have a square matrix, and then if one of these statements is true, all the rest are true. They all say this. They're all telling us the same thing. The following statements are equivalent. So if we could say the reduced row echelon form of A is the identity matrix, or we could say A can be written as a product of elementary matrices, or we could say A is invertible, or we could say AX equals 0 has only the trivial solution X equals 0. Or we could say AX equals B is consistent for every vector B in Rn. Or we could say AX equals B has exactly one solution for every vector B in Rn. Okay, so this is saying to us, this statement here is saying there is a solution. And then this statement here is saying the solution is unique. Okay, we have proved A through D, and I will simply direct you to our textbook. E and F are proved in the textbook. See page 117 of the Busby textbook. Okay. All right, main message here for this lecture is that there are these things called elementary matrices. Every elementary matrix has an inverse, and that we can use that idea to find the inverse of A by forming the compound matrix like this, A, I, row reducing down till we get to I, and at which point we are going to be able to see the inverse right there. Okay, so that's the idea. Great, thanks a lot, and I'll be back with the next search section shortly. Bye.